Hello, this presentation will talk about piecewise Bezier curves. You can find it in the textbook in section 8.4. By a piecewise Bezier curve, what we mean is a long curve formed by joining together multiple Bezier curves. So we're going to use multiple degree 3 Bezier curves to form a longer curve Q of U. And this will allow us to make curves Q of U with lots of bends and turns and so on, more than can be done with a single degree 3 Bezier curve. So let's draw an example of this with 3 pieces. We'll start off, the first piece will be called Q1, and it'll start at P0 and end at P3. The second part will be called Q2, and the third part will be called Q3. And we'll let the control points for Q1 be P0, P1, and P2. So Q1 is a degree 3 Bezier curve by itself. And Q2 is also a degree 3 Bezier curve by itself. And its control points will be, I'll call them R0, R1, R2, and R3. And likewise, Q3 is a degree 3 Bezier curve, and its control points will be S0, S1, S2, and S3. And altogether, these are going to make a longer curve, which I'll just call Q. So let's first draw the control polygons for these 3 Bezier curves. The control polygon for Q1 starts at P0, goes to P1, to P2, and finally to P3. So these 3 straight line segments are the control polygon for Q1. For Q2, the control polygon starts at R0, goes to R1, to R2, and to R3. And finally, for Q3, its control polygon goes from S0 to S1, to S2, and finally to S3. And we're going to use the fact that these control polygons join up smoothly to later on to talk about having a smooth curve. But first, let's talk more about just Q and its continuity properties. The whole curve, Q of U, will have domain 0, 3, formed by sticking together Q1, Q2, and Q3. So we're defining Q1, we're defining Q, to be Q1 of U if 0 is less than or equal to U is less than 1, to be to Q of U minus 1 if 1 is less than or equal to U is less than 2, and Q3 of U minus 2 if 2 is less than or equal to U is less than or equal to 3. So in this example here, the domain of Q of U is 0, 3, and we're treating each Qi as domain 0, 1. So the point of these minus 1, using U minus 1 and U minus 2, is for U greater than 1, U minus 1 is back in the range 0, 1, and for U greater than 2, U minus 2 is back in the range 0, 1. And we'd like to start off with continuity properties. We want Q of U to be continuous. Well, it's formed from 3 continuous parts. Each of Q1, Q2, and Q3 by itself is continuous, so we just need to check that they join up at a common point when we transition from Q1 to Q2 and when we transition from Q2 to Q3. So for this, we need to have Q1 of 1 is equal to Q2 of 0, i.e. P3 is equal to R0, because P3 is where Q1 ends at U equals 1, and R0 is where Q2 begins at U equals 0. And we need Q2 of 1 is equal to Q3 of 0, i.e. R3 is equal to S0, because Q2 ends at R3 and starts at S0. If we have these things equal, then Q will be continuous, and it's an if and only if condition. So we're just going to assume henceforward that our curve is continuous. Otherwise, it breaks into two pieces, and we would treat it as two separate curves. Just continuity doesn't tell us anything about the curve being smooth. It just means it's continuous. There's other things that could happen with continuity. So we could have, for instance, a corner. In other words, we could have, let's draw a picture. We could have Q1 like this, and Q2, say, like this, and they join up there. Although they're continuous, the ending point of Q1 is the beginning point of Q2. They don't have continuous derivatives or continuous slope, and we'll have a corner there. We could also have a cusp, which is a variation on the corner, which is something like this. And again, this is Q1, and this is Q2, and this would be a cusp where the two curves come together tangent to each other. And this would be another example of where, although Q is continuous, it doesn't have continuous derivatives. So we'll talk about continuous derivatives on the next board. So let me draw the slightly simpler case where we just have two curves put together to make one curve. There's Q1, which has control points P0, P1, P2, and P3 again. And then there's Q2, which has control points R0, R1, R2, and R3. And let's assume that R0 equals P3, so the curve is continuous. So we'd like it also to have continuous first derivatives. For continuous first derivative, and this property is called C1 continuity. So C1 continuity, the 1 means first derivative. It means that the curve is continuous and its first derivative is also continuous, or first derivative is defined and continuous. So but for continuous first derivatives, we need that Q1 prime of 1, the derivative of Q1 at U equals 1, is equal to Q2 prime of 0, the derivative of Q2 at 0. So in other words, we want the derivative, the rate of change of Q1 of U as you approach its endpoint P3 to be equal to the derivative of Q2 on the other side of P3. So we want to match up the first derivatives. What this means then with C1 continuity is we can think of this as useful, I should say, let's think of U as being time. This is useful for Q of U defining some position or some other aspect of motion as a function of time, with U representing the passage of time. So in other words, with continuous first derivatives, if you're moving along the curve Q formed by putting together Q1 and Q2, if Q of U gives you the position on the curve, your velocity will be a continuous function. You won't get jerked around or any sudden changes in velocity and so on. So what do we need for C1 continuity? We need that Q1 prime at U equals 1 is equal to Q2 prime at u equals 0, and q1 prime at u equals 1 is equal to 3 times p3 minus p2. And q2 prime at u equals 0 is equal to 3 times r1 minus r0. In other words, to get the equality, we need to have p3 minus p2 equals r1 minus r0. And of course, recall that r0 is equal to p3. So in other words, p3 minus p2 equals r1 minus p3. In pictures, what are these vectors here? So p3 minus p2 is this vector here, tail at p2, head at p3, joining the next to last control point of q with the last control point of q. And r1 minus r0 is this vector here. Should have been drawn a little more collinearly. Let's just assume they're drawn collinearly there. So we need that this vector between the first two control points of q2 is equal to this vector between the last two control points of q1. And that's in fact, necessary and sufficient condition to have C1 continuity, to have continuous first derivatives. So this is what we want if we want to have smooth motion, with the motion being defined by a piecewise Bezier curve. Everywhere we transition from one piece to the next piece, we need to have this kind of property on the control points. Now, we don't always use Bezier curves or piecewise Bezier curves to define motion. Sometimes we just use them to define static shapes. And then we don't need C1 continuity, but a weaker concept known as G1 continuity, which I'll talk about on the next board. G1 continuity will be used to talk about piecewise Bezier curves that have smooth slope, even if they don't have a smooth rate of motion. C1 continuity was used to say that if you have a particle moving along a curve with time controlled by u, that it has no jerks and jolts. But we often don't care about a curve as defining motion. We just care about a curve defining a shape. And when we have a curve defining a shape, we don't care about the velocity of a particle moving on the curve at all. We just care about the overall shape of the curve. So this is G1 continuity, and G stands for geometric, and the 1 stands for analogy to first derivative, although it doesn't really have anything to do with derivatives. An example of what I'm talking about is we might have a curve with two pieces. And the control points could be, for Q1, could be P0, P1, P2, P3. And for Q, this is Q1. And for Q2, they could be R0, which is equal to P3, R1, R2, and R3. So this, as drawn here, is not really C1 continuous. Maybe I should exaggerate that a little bit more. Let's put R1 a little bit closer here. And the point is that if you draw P3 minus P2, and you draw R1 minus R0, those two vectors are not equal. So we do not have continuous first derivatives at u equals 1. So here we want to have continuous slope, which I don't want to give a formal definition of. In fact, this isn't really quite the right way to put it. But what we mean by this informally is that as one moves along the curve, the slope is continuous. In other words, the curve looks like a smooth curve without any corners and without any cusps. So there's no corners and no cusps. There's a formal definition of this in the textbook, which I don't really want to cover here, but I just want to say informally, this is the idea, and even the word slope should be interpreted in a sort of generous way, because we do allow also vertical slopes to happen. So we could have the curve moving straight upward where there's no actual slope, the slope would be infinity. But again, we have a notion of direction, and we really want to say the direction is continuous. What we need for this is, here's a sufficient condition, and it's what's pictured over there on the board, right here. Its sufficient condition is that Q1 prime of 1 is equal to some positive multiple, I should say, of Q2 prime of 0, where this, okay, the first derivative of Q1 at 1, so that's the first derivative of Q1 at the end of it, is alpha times the first derivative of Q2 at its beginning, where alpha is greater than or equal to 0. Sorry, alpha is greater than 0. We don't want to allow alpha equal 0. And in fact, Q1 prime of 1 is non-zero. And the derivatives, I should be clear here, are vector value derivatives. The derivatives themselves are vectors. So Q1 prime of 1 is not the 0 vector. So for this condition, we need that the 3 times P3 times P2 is alpha times 3 times R1 minus R0, with alpha greater than 0 and both sides of the equality non-zero. That is to say, we need P3 minus P2 equals alpha times R1 minus R0, which is the same as alpha of R1 minus P3, where alpha is greater than 0 and P3 minus P2 is not equal to 0, so P2 is not equal to P3. And this is sufficient for G1 continuity. If we have this condition, the curves will join up smoothly. So the next presentation will talk about a structured way to join piecewise Bezier curves together to interpolate certain types of points. And we'll talk about that in the next video. That's the end of this video. Thank you very much.